Hmm? Say it again.
Like I saw your mail like yesterday.
Yeah.
I didn't see the previous mail where you asked for like whether we.
No, that's okay. I just want to know whether, I mean, if one person hasn't done, then I have to do it. If everybody, so I just want to know. Possibly you could have read or something. That's why I asked. Okay. So today we will discuss polar decomposition. Say, huh? I'm not sure. You know it. Okay, no problem. Maybe do you know that if the polar, I mean, if an operator X is in fundamental algebra, the polar decomposition also in the. Okay, fine. So that's okay. Anyway, we'll discuss it. So before discussing polar decomposition, I have to define what is a partial isometry. So this is in terms of partial isometry. So this is the proposition. We have an operator, maybe alpha u, because I want to. This proposition defines partial isometry. Okay, so u is b of h. Then the following conditions are equivalent. First condition is u looks like this. U satisfies this equation. Second is u star u is a projection. This is the actual definition we want to use. Okay. If u star u is identity, then we call it isometry. U star u is a projection, then it is a partial isometry. Is a projection. So u star u is a projection. The third condition is this will justify what it means by partial isometry. So u restricted to kernel perp of u is an isometry. Is an isometry. And if you restrict that operator, that just means that u xi u eta equal to, it satisfies. Isometry means it preserves the inner product. Kernel perp of u. Okay. So proof. Actually, the polar decomposition, once you know the definition and all that, polar decomposition is just a what is usually called as a tautology. It is just, there is really no proof involved. You just write it, it is precisely that. Okay. I mean, so there is really not much. Even the uniqueness statement, everything is the statement itself. There is really not much idea is involved, creativity is involved. It is direct. Okay. So 1 in 2. If it satisfies u equal to this, then u star u, that is if u equal to u star u, then this is equal to u star u star u. Then this is equal to, that's all. That's what this means. And it's also true that u star means u star u. So u star u is a projection. So this is clear. And 2 implies 1. So if u star u is a projection, then we want to prove this. Okay. So for that, so u star u is a projection. U star u is a projection. Then, okay, I have to prove something. We haven't done that. Okay. I'll prove it as a separate lemma. I think lemma proposition itself. We want to prove that kernel of u is equal to kernel of u star u. Okay. In fact, we will do this. Kernel of u star u power half. This is a positive operator. U star u is positive. Any t star t is positive. Okay. This is for general u. Maybe t. We will use t rather than u. Any t then this kernel of t equal to kernel of t star t power half. I mean, this follows easily equal to kernel of t star t. Okay. Of course, this is to range perp of t star, right? Range perp of t star. This is right now, yeah. So kernel of t star is range t star closure. Okay. So now we want to prove this. This is clear. So we have this, of course, norm t x square equal to inner product t x dx. This is equal to, you bring it t star t xx. Of course, we know the square root is this. When t star t is positive, the square root exists. This is equal to norm t star t for half x square. So this implies kernel of t is same as kernel of t star t power half. But on the other hand, we want to prove that this is equal to kernel of t star t. So how do you prove it? Direct is by Weierstrass theorem. Direct is polynomial Pn, which converges to root t. This function root t. Okay, any continue. So with Pn of there is no constant terms. Pn of 0 equal to 0. If you don't like it, there exists Pn which converges to root t, then you just take Pnt minus P of 0. Pn of 0. Pn of 0 should Pnt converges to root t, then Pn of 0 will converges to root 0. So this will, I mean, you can replace it with this. Okay. So there exists polynomial. So this implies Pn of t will converges to t power half. This is true for any positive operator. T is greater than or equal to, if t is greater than or equal to. Okay. So this implies Pn of t star t converges to t power half. I mean, t star t power half. Okay. Well, maybe you take it yes. Yes, positive. Okay. Yes, 0. In particular, this is true for Pn of t star t converges to this. So now first, if t star t power half is 0, I mean, if t star t power half xi equals 0, this implies, of course, t star t xi equals 0. So one way is clear. We have to prove t star t xi equal to 0, that this. Okay. So if t star t xi equals 0, this implies Pn of t star t equals 0. Okay, for all n. Since Pn of 0 is 0. This will be true. So this converges to that. So this implies t star t for half is also 0. So this proves this statement. Okay. Now this is equal to this, and this is equal to this is we have seen, and these are all equal to this. Okay, we have already seen all this thing. So from that, now use this. Okay, what do we want to prove here? U star. So we want to prove U star U is a projection. U star U is a projection. Is a projection onto, I mean, range of, if you want, kernel perp of U star U, which is equal to, of course, I mean, it's a projection on range of U star U, of course. Range of U star U, which is closed, which is equal to kernel perp of U star U, which is equal to kernel perp of U, of course. Now we want to see what is U star U. So now xi is in H, and xi is equal to xi1 plus xi2. You call this as H0, okay, where xi1 is in H0 and 2 is in H naught. H naught is the range of the projection. Then you can decompose any xi as xi1 plus xi2, where that's in the orthogonal complement. This. Now you just, and similarly eta. Similarly, eta equal to eta 1 plus eta 2. Now you just say this, use u star u xi1 plus xi2, not product eta 1 plus xi2. I will go fast. Now u star u of xi2 is 0 because that is in the kernel of the range. So this only this will survive. So this is equal to, but then on u xi1, u star u xi1 is xi1 itself because it's a projection. So the whole thing is just u xi1. Okay, and u xi1, but then u xi1 is in that range H naught, right? So E2, eta 2 is orthogonal to this, and I mean, we don't need, this is just equal to eta 1 plus eta, it is just equal to this. Okay, that's all. Same thing. It does. Okay. So this implies u equal to u star u. Okay. So 2 implies 1 is clear. Now we will do two implies 3, and we will quickly do 2 implies 3 and 3 implies 2. So if u star u is a projection, then we want to prove again, let xi is in that H naught. H naught is same as this is equal to range of u star u. Okay, and we want to prove that it's an isometry on this. So we want it preserves inner product on this. So let's take xi and eta, to xi and eta on this. Okay, now u xi u eta equal to u star u xi eta. Now this is in the range, so this is just equal to xi eta. Okay, this is done. Clear. Right? This is clear, no? If I make a mistake, you tell me, because I'm going fast, I may make mistake. But even then, it's all exercise, you can do it easily. So now 3 implies 2. So now u restricted to, so this, I mean, we want to prove that 3 is u restricted to that space, range of, see, you want to prove, but then range of u equal to kernel perp of u star, range of u equal to kernel perp of u star, right? And that is same as range of u, no, kernel perp of u, sorry. That is not it, sorry, not on range of u. You want to prove that u restricted to kernel perp of u, it's isometry, and that is equal to range of u star u, okay? Range of u star u bar, and range of u star u closure. But then it's already closed because it's a projection, it's already closed. Okay, so so 2 implies 3 is clear. 2 implies 3 is if u star u is a projection, then u restricted to kernel perp of u is an isometry. Okay, so kernel perp of u is range of u star u. Now we take an element in 2 elements in H naught, which is the range of u star u. This is equal, which is equal to kernel perp of u. I have to prove that it preserves the inner product. It preserves the inner product. Just write it, preserves the inner. So now 3 implies 2. So if that is an isometry, u is an isometry, then we want to prove u star u is a projection. That's the only thing left. Now 3 implies 2. So now we have u restricted to kernel perp of u is isometry. Then u star u is a projection we want to prove. So you take xi eta in, I mean, xi eta in H. What do you want to prove? We want to prove that u star u is a projection. Okay, so u star u acting on any xi, we want to check. Okay, where xi eta is in this, and xi is equal to xi1 plus xi2, and eta equal to eta1 plus eta2. We decompose it like that, where xi, xi1, eta1 are in that kernel perp of u. Okay, and xi2, eta2 are in kernel of u. Okay. Okay. Now U star U xi eta. This is the projection you want to prove, which is equal to U xi U zeta. But then this is equal to U xi 1 U eta 1, because on the kernel it is 0, of course. That decomposes into kernel and kernel perp. No, on xi 2 it is 0, eta 2 it is 0. So this is, but this is just equal to xi 1 eta 1. But then this is also equal to xi 1 eta 1 plus eta 2. Because eta 2 xi is xi 1 is 0. Okay? So all these things imply U star U xi equal to xi 1. So it's a projection onto. So U star U projection onto that kernel perp of. Okay. I decompose xi and eta like this, then I check the inner product to prove some operator is a projection. To prove that if you decompose into two subspace, on one subspace, on one subspace is identity, the other orthogonal complement is 0. And that happens clearly. Okay. Okay. So any operator satisfying any of one of these properties is called an isometry. It's a partial isometry. U satisfies any one of them, 1, 2, 3. Then U is called as a partial isometry. And corollary to this is U is partial isometry. Then U star is also a partial isometry. That's clear from the first condition. U taking star, U star will also satisfy the first condition. So from that it follows that U is partial isometry, U star is also a partial isometry. In particular, if U star U is a projection, U star is also a projection. Okay. Let's just have a small discussion. What is an isometry? See, usually, what is an isometry? You have a Hilbert space, and a Hilbert space is not a set. Just for our convenience, I'm saying. You have a isometry. This is some sort of, you take it as a fiber kind of. It is just it's defined on the whole Hilbert space, and the kernel is 0. Kernel is trivial. Then it goes to the range as there is a range of U. U is from here. Okay. Then there is this range perp. Okay. And range perp. So this is the range perp of U. This is range of U perp, which is equal to kernel of U star. This is equal to kernel of U star. So U star is injective here, and it will be an isometry here. So if you define an isometry from which is on the whole space, it will land up here in the range. And from here, U star will be from here, which is an isometry here, and it is 0 here. Okay. This is a U star is called a co-isometry if U is an isometry. What is partial isometry? Partial isometry, you have two. So this is partial isometry. U is partial isometry. Partial isometry. That means you have this kernel of U, okay, and this is supposed to be kernel of U. This is range of U, okay, and this is kernel of U star. Range perp is kernel of U star, and this is range of U star. Okay. Range of U star. This is range of U star. This is, I mean, so this is, so U acts here. This is kernel of U, so it is 0 here. And this is range of U star. Range of U star is where, which is equal to the kernel of U perp, of course, kernel of U perp. So here it is isometry. This is third condition says. So this is here it's isometry and it's land sub here. So if you remove these two spaces, this is just an isometry between these two spaces. That is for partial isometry. Partial isometry is you remove these two spaces. Okay. One here it is just range of, here you take range of U star U, here you range of U star. Okay. And this is just the partial isometry is just an isometry between range of U star and range of U star. Okay, that is how we should understand. Okay. So you can even forget all the things. It is basically this. Partial isometry, it just you take the projection U star U, okay, and take the kernel. I mean, so you remove the complement, and here you take the projection U star. Okay, you leave out the complement. It is just an isometry between these two. Okay. That is partial isometry. Okay. So okay. So if we need, I will say more about partial isometry later. Okay, if we need any other topic. Okay. So we want to prove the following theorem, which is called polar decomposition. Which is very similar to the polar decomposition, you know, for complex numbers. If you have a complex number Z, it can be written as R is greater than 0, and this e power I theta has whatever it is, mod 1. Okay. So you should write here as you are, whatever. So here, for any first statement is for any t in B of x. Okay. There exists a partial isometry U and a positive operator let's say A greater than or equal to 0, such that U equal to TA with, sorry, kernel of, yeah, kernel of U equal to kernel of T equal to kernel of A. Okay. And with this condition, kernel condition is unique. That is the statement. The second statement is if there exists another partial isometry V and B greater than or equal to 0, such that T equal to VB and this kernel condition is satisfied. Kernel of T equal to kernel of B equal to kernel of V. Okay. Then V equal to U and B equal to A. Okay. Whatever. Both looks like me. U equal to V and A equal to B. I mean, this A, whatever A or B, whatever we say, this will be equal to square root of T star T. Okay. So the importance of polar decomposition is, suppose if you can prove some T equal to UA, then that will be the polar decomposition. A will be equal to mod T and the partial isometry. I mean, this is uniquely associated to this. Okay. So we can talk about the partial isometry, the positive operator, the polar decomposition. So maybe I will write that A is nothing but T star T or half, which is also same as mod T. Okay, mod T means, I mean, the modular function. You can associate a modular function. It's a continuous function. So using continuous functional calculus, you can call it mod T, and it is exactly that. Okay. Continuous functional calculus. T star T. Ah, okay. T is not an operator, but T star T is an operator. Okay. You call it mod T. Okay. When it is T is normal, this is the continuous functional calculus. Yeah. Yeah. You're right. Okay. Proof. As it is just that writing the operator so that it's the same thing. We have the following Tx, Ty equal to, of course, T star T, Xy, and that is equal to T star T power half X. We have already seen this, T star T power half Y. Okay. We have already seen this. So which is same as, I mean, what mod Tx, mod Y. Okay. And we have our earlier, I mean, we have used this lemma several times. Even if you have a total set where the inner product is preserved, then the span closure, it extends to a unitary, that whatever the relation you have, that extends to the span closure. So this function and span closure mod Tx, no, I want the other way. Going in this relation, you can is a, well, isometry is enough, but maybe isometry. Okay, so isometry on range of mod T. Okay. You take the range of mod T. Okay. On that, you can define this U naught. And let P be the projection from H to range of mod T. I mean, you can talk about this on closure also, because if it is isometry and then, I mean, it extends to the closure. No? So this Tx, Ty equal to mod Tx, mod Ty. So I take from here to here. Okay. Then the function going mod Tx, I mean, sorry, this is mod Tx, sorry, not mod Tx. That has no meaning. Mod T acting as U0 of mod Tx going to Tx is an isometry and range of mod T. But then range of mod T closure is equal to kernel mod T. Kernel perp of mod T. Of course, this is self-adjoint mod T. Okay. So this is P is a projection onto range of mod T. Okay. Then U equal to P U0. Sorry, U0 P. P projects onto this range of mod Ts, and on that you take this. Now, P projects onto range of mod T, and range of mod T, you use that U naught. Okay, you call that as U. Okay, it's clearly a partial isometry, no? It is a partial isometry defined on it's a which initial space this and range purpose there is a partial isometry. Partial isometry. See, here I explained this. This is what is called initial space of the partial isometry. This is what is called final space of the partial isometry. Okay. So it's a partial isometry with initial space. Range of mod T closure and final space range of T. Sure. For something to be a partial isometry, it should just be isometry on subspace, right? That's what it means. It's just an isometry on the subspace, and it is 0 on the space orthogonal to that. I mean, it's so for something to be in partial isometry, it should be isometry on the kernel perp of that. Okay, so clearly this is, I mean, this P is a projection onto this. The kernel perp is the, I mean, the and the kernel perp of this will be exactly the orthogonal complement of this, where that is 0. And on this is isometry. On this P applied on this is just identity, and U0 is an isometry. So this is clearly an partial isometry between initial space this and final space this. And you just write the definition. Now U acting on mod T, acting on S is just Tx by definition, right? U acting on any mod Tx, P of mod Tx is just mod Tx itself. And U not acting on that is Tx, that's how it is defined. So there is, as I said, there is really nothing. You have an operator T, then you notice that this relation is satisfied, which is a very trivial relation. From that, it follows that from here to here, it preserves, I mean, this is an isometry. Then you write it such a way that U mod is equal to this. It's a direct relation. So this factor. And it is clear that this U, kernel of U is that kernel of P, which is same as the kernel of, I mean, kernel of that mod T, right? Mod T is self-adjoint. I mean, mod T star it should be, but mod T is self-adjoint, so it is the kernel of that. That is clear. Okay. Okay. So now we want to see the uniqueness. So suppose T equal to UB, VB with kernel of T equal to kernel of V equal to kernel of B. Okay. Then let's just, we first show that B is nothing but T star T, and B is nothing but square root of T star T. B is positive, so we have to show that B square equal to T star T. We want to prove, I mean, in our case, we have the first case, we got that our A is nothing but T star T power half. In this case, we know that A is nothing but T star T power half. So we want to prove that this is, I mean, this is unique means we have to prove that we have to show that this V equal to that U. Okay, whatever that we defined as U. And B is whatever we defined as A, which is square root of T star T. So we have to prove that B is T star T. To prove B is T star T, we just T star T power half, we only have to prove B square equal to T star T. Okay. So let's consider, let's consider T star T, that is equal to B star V B. Okay. Now V star V. So now we have the kernel of V, which is equal to kernel of V star V, which is equal to kernel of B, of course. Okay. Right? So on range of and B is positive, so I mean kernel B star and B doesn't matter. So on this acting on, I mean V star B acting on range of B is identity. Because range of B equal to kernel perp of B, okay, because it's self-adjoint. That is same as kernel of V star V. Okay. Kernel of B is equal to kernel of B star V. Kernel perp of B is kernel perp of B star V, which is same as range of B star V because it's a projection and because, okay. So from all these things, this is equal to B star B because B star acting on B is identity. Range of B is identity. V star V is a projection because kernel of V equal to V, kernel of V star V equal to this. Okay. And this is equal to, so this implies kernel perp of this equal to range of this equal to range of this. B is self-adjoint. Okay. So this implies B star B, that is equal to B square, of course. B is self-adjoint. So this implies B is equal to T star P power half. So that we have proved. Now we have to prove that B is same as that U. Okay. I mean, that is again tautology. B is same as that U. Further, we only need to prove B is equal to U. We need to prove V acting on mod T X equal to, I mean, we know that, I mean, we mod is VB X. This is equal to TX. Okay, right? I mean, we know that now B is mod T. So V at mod TX equal to this TX. On the other hand, V acting on some other Xi, where Xi is in range of mod T per, mod T, range of mod T per. Okay. Then this is just, I mean, we know that kernel of V is same as kernel of mod T, no? This is equal to 0. Since this is equal to kernel of V also. All these kernels are same. Okay. All these things have a kernel same. So this is just V of Xi. The Xi is in the, I mean, this is equal to kernel of mod T, right? V acting on this per. See, we want to prove that V is same as U. U takes, we know that mod Tx to Tx. And of course, on the kernel, on the orthogonal complement, it is 0. V also does the same thing. V acting on mod Tx by definition is Tx. And the orthogonal complement, it is 0 because they have the same kernel, right? They all have the same, I mean, whatever the operator you deal with here, they all have the same kernel. You don't even have to worry, which is what, okay? So this implies U and U equal to V, okay? V equal to U. Okay, so this is a remark. If T equal to UT, U mod T, polar decomposition, then we have U star T equal to mod T. Okay? Just we have to remember this formula. We may use it. That is clear, no? Because U star T equal to U star U mod T. U star T is a projection, and it's a projection onto range of T. Okay, so this is equal to mod T. Because U star U is a range on projection onto the range. I mean, U star U, the partial isometry here has the initial space, this range of this, and final space, the range of T. Okay. To know a partial isometry, you only have to know the initial space and the final space. The initial space of this U is range of mod T, and the final space of this U is T itself, a range of T. Okay. So that's all. Okay. So we have proved polar decomposition. Okay. Okay. So if T is invertible, then I mean, if T is injective, you will get that U is isometry because of the kernel, right? I don't have to write all that. If T is injective, the kernel is 0. The kernel of U is also 0. That means U is isometry. Okay. Also, if T is invertible, it's also surjective. Okay, then U has to be surjective. U will be unitary, right? I mean, yeah. So, but still, at some point you will get unitary. I mean, you will not get polar decomposition, but something like this, T equal to UT with U as unitary. When dimension of T and T star, I will leave it as an exercise. I mean, okay, you should think about it. So when you will get, if and only if, when you will be able to get a unitary. What I am saying is, the T can be written as a unitary times mod T. Okay? When you can write like this. This is not polar decomposition. Okay? T may need not be invertible. Okay? If T is invertible, U is unitary. Okay, that's clear from the, you will get the polar decomposition, you will get unitary. Okay, but even without that, you will be able to get it as get a unitary. You will be able to write like this. Okay? With this is unitary and this is mod T. Okay, when you will be able to do, you think about it. Okay? I actually said the answer. Think about it. When I say I think about it, I may ask it in the exam. Okay. So. Now we want to come to our von Neumann algebra. So so for von Neumann algebra, the elements in the von Neumann algebra will use small letters. So this is proposition. Let M be a von Neumann algebra. X in M and X equal to U mod X, polar decomposition. Then U mod X both in M. Proof. Of course, clearly mod X equal to X star X or half. Of course, this is clearly in M because it's a von Neumann algebra. X star X is there. And if you X is in that, the von Neumann algebra generated by C star algebra is generated by that is in M, of course. So C star algebra generated by X will contain the square root. Right? That's all continuous. I mean, it's all continuous functional calculus. So, so that will be there in M. So this is clear. You only have to prove that the partial isometry is there. Okay. So to prove U is in M, we need to U is in M double commutator. Okay. So that is U is in the commutant of the commutant. Okay. So let X prime is in M commutant. We have to prove that U commutes with this. Okay. So this is the nice thing about one another. You can do all that. So X prime is in the commutant. We have to prove U X prime equal to X prime U. Okay. Let us just compute it. So we have X equal to U mod X. And we already know that mod X is in M. Okay. So X prime will commute with mod X because it's already in M. Okay. So now U X prime X. So let Xi is in H. Okay. Then we want to prove what we want to prove. Okay. So So what we do is the following. Let's say it's right mod P. Okay. Rotor. And Xi2 is in the curve. Okay. Curve. Okay. We can decompose it like this. And we have to prove that u x prime equal to x prime u on Xi1 and Xi2 separately. Okay. Okay. Let's just write it for a general one. X prime x prime equal to x. Okay. Now, I think I will calculate this. X prime x prime x xi equal to, we have this, okay? We have this. From that, we have to conclude that x prime x xi equal to x prime u mod x xi. Okay. Okay. Okay, that is just that x prime u mod x, u mod, I mean u mod x xi. Let it be. And we have to prove that x prime xi equal to u mod x x prime xi equal to this commutes. So u x prime mod x xi, right? So these two are equal. X prime xi equal to x prime xi. Okay. So I just compute this and I get this. I just compute this, I get this. Okay. So x prime u equal to u x prime on mod xi. Okay. So this implies x prime u and u x prime on range of mod what mod x mod x. There is no t. This is mod x. Okay. On range of mod x closure. Okay. On range of mod t, so it's extends, the relation extends to closure. So we only have to worry about the kernel. And we don't need to decompose like this. This is not needed. We just separately check it. Okay. So we have proved that this relation x prime u equal to u x prime on range of mod x. Now we have to verify that on the kernel of mod x also this is true. Okay. So now let xi is equal to the kernel of mod x. Okay. Then, of course, kernel of mod x. So, I mean, u mod x xi. What do you have to prove? I have to prove that u x prime xi kernel of mod x. So u, okay, let x prime u xi equal to 0 since mod x xi is in kernel of u also. Okay, kernel of u and kernel of mod x is same, right? Because it's polar decomposition. This is equal to kernel of mod x, right? Polar decomposition, all the three operators, the operator, its partial isometry, the positive operator, everything has the same kernel. So kernel of mod x and kernel of u is same. So kernel of xi is in kernel of mod x means xi is in kernel of u also. So u xi is 0. So x prime u xi is 0. We only have to prove u x prime xi is 0. Right? So it remains to prove. Right? Clear, no? Okay. I mean, I have proved that I want to prove this relation, right? I have an x prime in M. I only have to prove, we need to prove u x prime equal to x prime u. That's all. Okay. I proved that u x prime equal to x prime u on the range of mod x. Okay. On the kernel of mod x, I have to prove. Kernel of mod x is same as kernel of u. So this is 0. So we want, it only remains to prove the other equation. Other one is also 0. So now we want, so it remains to prove so it remains to prove u x prime xi is also equal to 0. Okay, that's what you have to prove. Okay. So let xi is in kernel of mod x. Okay. Now is in kernel of mod x, then x prime of x prime of mod xi. Okay. Mod x prime of ux prime equal to 0. That's what you have to prove. So x prime is mod xi, then x prime xi is also in so I mean we prime that x prime, claim that x prime xi is also in the kernel of that u, which is equal to kernel of mod x. That's what you have to prove, right?
Yeah.
That follows from the commutativity. That's all. So so x prime xi is also in the kernel of this. So mod x times x prime xi equal to x prime mod x xi equals 0. That's what we need. We have to prove that u x prime xi equal to 0. So x prime xi is in the kernel of u. That's what we have to prove. So it's enough to prove x prime xi in the kernel of mod x. Okay. So that is what is proved here. X prime xi in the kernel of mod x. So x prime xi, I take mod x on this, x prime mod xi equal to 0. Use the commutativity and you get this. That's all. So if x is in the von Neumann algebra, then the polar decomposition is also in the von Neumann. Okay. So I will stop here, a short class. We will start tensor product and classification of time. And it's all same topic. So we'll do it tomorrow. Classification of type 1. You haven't seen tensor product, no? Hilbert spaces. I don't think you would have seen. So, by? About tensor product. So why is he doing that? So, but why is he doing that? It's not needed, no, anywhere. To Hilbert-Smith, he's doing Hilbert-Smith operator.
He's just giving examples
Examples for what?
Examples of different Hilbert spaces.
Okay, you tell me what he does. So I will. There are different ways of defining it. See, it's tensor product. You can just define. You take H1, take H2. You can define an inner product on just a product of. I mean, you take formally you take something like this. You can define an inner product on that and take the closure. There is another thing called positive definite kernel, which is better to do through that. Okay. So I will do that. Which positive definite kernel. If you have a positive definite kernel on a set, then you can construct a Hilbert space corresponding to that set and positive definite together. Okay. So here you have a H1, H2. You will have a set like this. I mean, this is very similar to Gelfand-Neymark construction. You have something, you define some inner product and take the kernel and close it. Okay. So that's a more general construction which can be used for many other purpose also. So I will do that. Then using that, I will define the tensor product, which will define clearly. Okay. After that, we will talk about type 1 phenomenon. We will classify it. Okay. So that's what we will do. That's class.